Let's do another strong form induction problem. And we're going to prove something that we've already talked about in this class a few times actually, but we're going to prove the fact that every tree with n nodes has exactly n minus 1 edges. Now, this could be a free tree, it could be a rooted tree, it could be a binary tree. Who knows what kind of tree this is? I'm saying every kind of tree with n nodes has n minus 1 edges. So how am I gonna prove that? How am I gonna back this up? And again, you could put a bunch of trees out there and you could count the nodes and count the edges and you could see that it's true for the trees that you do, but how do you prove it for every single possible tree? Induction is the way to do it. So what's our predicate gonna look like? Okay, we're gonna say let P of n be the proposition that this is true for a tree, for any tree with n nodes. All right, then we'll start with our base case. All right, is it true for a tree with one node? We'll not talk about the empty tree here, although you could. Is it true for a tree with one node? And the answer is, well, yes. A tree with one node, right, has no edges. Well, is 1 equal to 1 minus 0, right? It's n equals 1. N nodes is n minus 1 edges. It has one node, is 0, 1 minus 1. Or hold on, I asked the wrong question, right? According to this, right, P of 1 is saying that a tree with one nodes has 0 edges. Oh yeah, that is right. Good. Now, what does our induction step look like? And this is going to be a little different here because we're going to look at a tree of size k plus 1, and we're hopefully going to prove that has k edges. But the way that we're going to do that is we're going to break up this tree. And we can't just break up this tree willy-nilly. We have to say any way that you break up this tree, it's going to work. That's why we're going to need strong induction, because maybe we break off the tree by taking off one node. Maybe we break off the tree by splitting it in half. Maybe it's like a 2/3, 1/3 split. Who knows? But we're going to have subtrees that are of size, any size, smaller than n nodes. All right, and that's why we're going to need strong form induction. So we're going to assume, right, any tree with 1 or 2 or 3 all the way up to k nodes has, one fewer edge than it does vertex, than node. All right, and we're going to try to show that if we have k plus 1 nodes, has k edges. All right, we're assuming it's true for 1, 2, 3, 4, 5, 6, all the way up to k nodes, that those trees will have one fewer edge than they have nodes, which is, again, another way of saying this. And we're trying to prove it for a tree with k plus 1 nodes. So, oh, I did not do this I didn't draw straight. Let's take this to the next page. Let's look at a tree with k plus 1 nodes. All right, so, imagine that we have some kind of tree. I'm just going to make up some tree. Who knows what this tree actually looks like? Maybe the tree looks like this. Remember, the whole idea about a tree is that, right, there can't be any cycles in tree, so we couldn't have put an edge here. We don't know what this tree looks like, but maybe there's k plus 1 nodes. All right, and again, the picture is not part of the proof. The picture is just to help us see what's going on. All right, now you could draw a picture as part of a proof, but it's not really the formal part of what's going on. It's mostly just, hey, let's keep track of what we're thinking about. So let's say, right, So we have a tree of k plus 1 nodes. How can we show that there are k edges? Because that's what we want to show. That'll prove our induction step. And we can use this blue fact that we're assuming. All right. Well, we're going to we know that it's true for smaller trees. So let's break this up into a smaller tree. And there's a lot of ways that you can do that. Imagine you remove any edge. So maybe you remove this one edge. Now you have two disconnected subtrees, right? Or maybe you removed this edge and you have two disconnected subtrees. You know, the nature of a tree is that no matter what edge we erase, if we erased an edge, would lead to us getting two disconnected subtrees, each one with fewer than k plus 1 edges. So if we remove, and the important part is that we're removing any edge, right? Then we have two disconnected subtrees. And the question is, how many edges do those subtrees have? Because if we remove an edge, and then we can count those individual edges, well, then the original one must have had those two plus 1, right? So we have two disconnected subtrees. Let's say each of these subtrees have K1 and K2 nodes in them. It doesn't matter, right? So for example, right, if we erase this edge, we'd have one subtree with 5 nodes and one subtree with 6 nodes, right? The original one had 11 nodes. Or, you know, if we did this one would have 2, one would have 9. It doesn't matter. What's important, right, is that K1 and K2 are both strictly smaller than k plus 1. So they're covered by the induction hypothesis. All right. We know exactly how many edges are going to be in a subtree of size K1. We know exactly how many edges are going to be in a subtree of k plus 2. And in fact, induction hypothesis is going to tell us that this is going to have K1 minus 1 edges. Tells us this is going to have K2 minus 1 edges. So, how many edges did this have? Well, it had this many edges, plus this many edges, plus the edge that we erased. Right? So our k plus 1 node tree has K1 minus 1 edges, plus K2 minus 1 edges, plus that edge we removed. What is that? Well, the minus 1 and the plus 1 cancel. We're left with K1 plus K2 minus 1. How does that help us? Remember, if we remove an edge and they have K1 and K2 nodes, I didn't comment on this, but what's the relation, right? Is that K plus 1, right? We didn't get rid of any nodes. So when you have two subtrees, right, the nodes of each subtree must add up to the nodes of our original tree. And our original tree had K plus 1 nodes. Again, we can think about this as here, actually I'm trying to color coordinate, but there's too many things, right? This would be like K1 is 6. And this would be our another subtree if we erased this edge. And that would be K2, which is 5. And K plus 1 is just adding these vertices together. This has 5 edges. This has 4 edges. So 5 plus 4 is 9, plus this one that we removed is going to be 10. That's the logic we're using here. So K1 plus K2 is just K plus 1. K plus 1 minus 1, of course, is just K. What did we want to show? We wanted to show we had K edges. And we just did that. All right. So we finished the inductive step. We've shown the base case. So we did base case, check. Induction step, check. So this predicate is true for all n, at least 1. Check by induction. And that's how we can prove it. So this is fun stuff, very powerful stuff. The last video on proofs that we're going to do is kind of talk a little bit more about what we did back here. About, well, when do you know to break things into cases, and what's some practice? How can we practice breaking up proofs into smaller proofs so that we can answer and figure them out and use things about those cases to get to the same result? That's what's coming up next. That'll be our last video on proofs. That'll be our last video in the chapter. That'll be our last video probably in the class.